double integral of the function f of xy is equal to 6 minus x plus 2y. That kind of lends itself to rectangular coordinates, at least based off of that. And oh boy, I hope this isn't a sign of things to come. Over the region bounded by the curves x equals y squared and y equals 2 minus x in the xy plane. All right, so that, you know, it's in terms of a setup, it's pretty straightforward. It's just, again, like everything else, what are we gonna do with this? All right, so we're looking at something that's not rectangular in terms of the base region. What I would do, you know, and I always kind of have this in mind, is I like to get a look. You know, and in this case, you can visualize what x equals y squared and y equals 2 minus x would be like, but I want to have something that's manipulatable. You know, I want to be able to just kind of rotate it as needed and go from there. All right, so I'm going to type in x equals y squared, and I'm going to type in 2 minus x, y equals 2 minus x. All right, so that little intersection of, well, the intersection of the two functions creates a bounded region. That little bounded region is the relevant one, right? That's all right, you know, this is our XY plane. And so that's, you know, we got a plane that's just kind of living up in space that is coming down in intersecting with the XY plane in that shape. So it's kind of like half of, I don't even know, probably like a pair, you know, I don't even know, it's something. But anyway, you could see the three-dimensional figure that I gave you. It has the plane in space and then that projection down onto the XY plane, right? So we got to look at it. Those two graphs are going to have an intersection. Might as well find out what that is. So I'm going to jot that down. So x equals y squared and y equals 2 minus x. All right, so do a little substitution. We have already, just brutal. So the x value could be swapped. X and y squared are the same thing. So y equals 2 minus y squared. So it's quadratic, so bring everything over to the same side. That's assuming you want to factor it, because you could just tap on those points to get the intersection. But I'm just going to kind of operate under the assumption that somebody in this room likes doing algebra. That's kind of a wise guy comment. I know a lot of people like algebra. So plus y minus 2 equals 0. And you don't get to this class unless you like math in some way, you know. So factors y plus 2 minus 1. For quality minus, fix it. And so you get y equals -2, +1, which is exemplified in those coordinates. All right. So Desmos is a great resource. This is not an algebra class. So your algebra skills, while wonderful, are not always necessary. So just keep that in mind. You know, not really concerned with those. Okay? So if you want to do the algebra, that's fine. I don't need to see it. Okay? So I just need the values. Now, as far as the integral is concerned, it's not a rectangular based region. So we got to be careful about this. What I'm going to do is I'm going to bring this in, snip it. The iOS version of snipping. I'm kind of a hoarder when it comes to that. I save these pictures and then I do nothing with them. But You got that. Now, it's a question of, we know it's going to be double integral. We can go triple integral if we want, but we have the equation solved for z in terms of x and y. So yeah, we can go straight for the double integral. We don't need to reinvent the wheel. So we know it's going to be 6 minus x. This is the ceiling function, plus 2y. It's just a question of, are we going to do the dx first or the dy first? And it really has to do with the bounds. So what we just figured out were y bounds. So this function is bounded in terms of y, based off of those intersections. It is also bounded in terms of x based off those intersections. So it's a question of, do I like the -2 to 1, or do I like the 1 to 4? And it could be a personal choice if it were rectangular, but in this case it's not. And so what I'm looking at is perspective. So if you think back to Calc 2, we find the difference between the dominant and the non-dominant function. This could get pretty complicated if we do it with respect to the x in terms of the bounding, because the intersection are numerical bounding. So the intersections wouldn't be relevant if we're talking about x, because the x, or the bounded region, would start here and end here. Right? Now, what you'd be dealing with is a case where the line is irrelevant over this interval, and it's only the parabola, the sideways parabola. Right? So if I were to work with numerical bounds, I'd first have to go 0 to 1, then break it up into a separate double integral from 1 to 4. I don't want to do that. So instead, what I'll say is, let's work our way up the line here. Because we have a consistent bounding over the interval of -2 to 1. So that's not a 2. That's a 2. -2 to 1. So my outer integral, which when we deal with rectangular coordinates, we want that to be the numerical case so that we don't lose variables along the way. That one would be -2 to 1, but my inner one would have to be the functions themselves, right? So it looks like I'm going dx dy. These would be my y bounds going from y equals -2 to 1. Now I just need some x bounds. Now those x bounds should be function based. Fortunately, we kind of already have that, right? So that linear function, this guy right here, yeah, it was given as y equals 2 minus x, but it could also be written, if I just move some things around, add x to both sides, subtract y from both sides, I could write this as x equals 2 minus y. Right, so we're just doing a little swap, switcherooski there. Right, now for the, I'm just making sure I want to do that in green. For the parabola, that's already given as a function of x in terms of y, so x equals y squared, so we're good to go there. All right, so we would be going from the lower function, which would be the leftmost function, in this case y squared, x equals y squared, to the upper function, which in this case would be 2 minus y. And that would be our iterated integral. All right, so this question is asking us to compute the double integral, so we got to do some work. I'll get rid of these because they're kind of distracting. So we work inside out. Integrate with respect to x. So 6x minus 1/2 x squared plus 2xy. That's happening over the interval of y squared to 2 minus y. We gotta do some substitution. Right? So every place, every instance in which there's an x has to get swapped out. We're talking 6 times 2 minus y minus 1/2 times 2 minus y squared plus 2 times 2 minus y times y minus all that stuff again, just swapped out for a y squared. Okay. So I'm going to move some things over. So 6 y squared minus 1/2, this would be y to the 4th, plus 2y to the 3rd. We can clean it up if we want, but what's the benefit? I don't know. The drawback to cleaning it up, well, for me personally, I don't want to speak for everybody else. I know that I'm probably going to make an algebra mistake. You've seen it happen many times. So let me take the algebra out of it and then focus on only possibly making a mistake where I type it in incorrectly. Right, so if I'm extra careful about that, I should be all right. So 2 minus y, close it up, minus, I'm going to go, I'll write the 1/2. I was going to go 0.5, but it doesn't matter. 2 minus, that's not a minus. 2 minus y, close it up, squared, double checking along the way. The next one I'll write is 2y, parentheses, 2 minus y. So kind of simplifying along, on the fly a little bit. And then, what I'll do is just kind of old algebra 1 style. I'll run through with the negative here. Oh, weird looking negative. So, sorry, my work never texts me, or my high school. Thought it was something important, but it wasn't. Well, I mean, I'm sure it is. It's just not any news. All right, so minus 6y squared plus 1/2 y to the 4th minus 2y cubed. dy. And we get a 15.3. That's exact, so kind of nice. And so there it is. And so, let the calculator do the heavy lifting when it comes to that stuff, the computational. Yeah. And besides, we're doing each other a favor, because if you don't do that algebra, then I don't have to go looking for mistakes in your algebra, right? Because anything you put down on paper that's incorrect, I have to rate, right? So if you put down something that's incorrect, I got to take off points. Maybe it's not a lot of points, but it's still something. And so just save both of us the effort. Right? I don't have to look at it. And then, especially with this, I mean, you got to clean it up. It's gonna take a couple of steps. It's gonna be messy. Oh, excuse me. I don't have to clean it. I don't have to look at it, and then you don't have to clean it up, and you get the right answer, and everything's good. Right? We're all happy.
Professor.
Yeah.
Sorry. Can you explain why the bounds for the x are 2 minus y and y squared, and not the intercepts?
Because the bounds need to be function related, because this is not a rectangular interval, right? So when you look at the graph here, if you were to say that it's just the just the x values of the x intercepts, what we would be saying, and let me just kind of steal some room here real quick. Get rid of images, lasso effect. if I were to say that it was going from, in terms of x, 1 to 4, I would be saying that it's going like this. So everything from, oh, geez, I can't draw. As you know, everything from 1 to 4 in terms of x. So all of this stuff. All right, with arrows on the end, right? Because it's going forever in each direction, right? And then for the bounds going from -2 to 2, I'd be saying that it starts here, extending infinitely, with the overlap being the bounded region of relevance. And what that would do is it would give us a rectangular interval. So I'd be looking at, let's see if we can get it decent here. Everything over this interval would be considered my base area. So we would be getting too much in some areas, in some parts, and too little in some other parts, right? Whereas, and let me just pull that out. And you know what? I can do this too. I'm gonna pop this back in here. Oh, that's weird. Undo, undo. How do I make that happen? All right, that took a little bit more doing than I needed. Anyway, that's what the bounds of 1 to 4, so -2 to 1 and 1 to 4 would give us. Dx dy. All right, so if you ever have constant bounds to a double integral, it's always giving you a rectangular base region. All right, whereas if you wanted to have something that's curvilinear, right, the part curve, part linear, option to have either, then what we would do is we would establish bounds based off of the difference between two functions first. So it becomes a question of, well, which functions do I want to bound, or do I want to use as the boundaries? So what I was saying is that I wanted to use the parabola. So I'll highlight that in yellow. Poorly. And I wanted to use the line. Yeah. But the question is, what parts? Because I can say, all right, well, I wanted to go from one to the other. So I could say that this guy is going from, and let me just move it down a smidge. I could say that this one is going from the y squared to the 2 minus y. But what part of the y squared to the 2 minus y? You know, because once we get beyond these x-intercepts, or I'm sorry, these intersections, then we still have a lot of interval that involves the difference between, or the interval between y squared and 2 minus y. All of this stuff and all of this stuff, which I don't want, right? What I want is only the values in between, right? In between the -2 and the 1. So what we do is we create a restriction by saying, all right, here are my fences, like literal fences, like fences that you would have in a yard, right? So I'm going to build my fences. One's going to be in the shape of a parabola and one's going to be in the shape of a line. It's going to contain a certain area. So then the person who's building the fence is naturally going to say, well, where do you want and how much do you want? And I say, okay, well, I want it at x equals y squared and x equals 2 minus y. How much do I want? How about we go from -2 to 1? right? And then, we were speaking the same language, the person would know, okay, so you're saying that for the x's, we want to go from the what I highlighted, I'm not going to highlight it again, the yellow, the parabola, to the blue, the line. But then I want to restrict that so that it only lives in this interval. It's only going from that -2 on up. So contained between these two functions, or bounded by these two functions, it's only going to be restricted between that -2 and the 1. Right? So it doesn't allow it to go all out here and capture more area than we need. Right? So in that regard, we would say that the y's go from -2 to 1 dy. Right? Now, you could go the other way and say, all right, well, what if I wanted to bound it between, if I write, instead of x equals y squared, I can write y equals plus or minus the square root of x, just solve for y in terms of x, and then say, okay, well, let that go in between 1 and 4. But the problem with that is we're shortchanging ourselves for a lot of area, right? So in this case, I gotta say, honestly, it ended up being, for me, and I hope it's not this way for everyone, but for me, in order to get the hang of this, I had to kind of experience not doing it the most efficient way first, and then realizing there's got to be a better way. And then once I did that, it was like, okay, so I look for the least complicated function pairing for the inner integral, right? So in this case, y squared and 2 minus y, something that'll capture all of the area cleanly, and then we create the restrictions for that. Right? But the one thing that you don't want to do, unless you know for sure that it's truly a rectangular region, is you don't want to go constant to constant, because if you do that, then you end up with what the integration is going to think is a rectangular interval, right? Rectangular base region. Right. I think we have another one that we can look at. So let me see if I can find that. It might be the polar stuff, but it's still kind of the same but different. The idea of deciding on your bounds is always what makes this the challenging thing. Because what happens is people they always come back with the same thing. They're like, oh, this stuff isn't bad if I can figure out the bounds. So let's see if we can kind of nail that down. So we did something similar to this one. This is page 80. We did something similar to this one with number 2. And there's a lot going on here, but it really comes down to the visualization and having a sense of, along the lines of the visualization or visualizing, whatever the right word is. What is the part that's relevant, So here it's saying compute the volume of the solid formed by the intersection of the surfaces, right? So I got 2 paraboloids. Now, they could be circular paraboloids, parabolas in 3D, or they could be elliptical paraboloids. We don't know, right? We could put it in Geogebra, but that's not really the point, right? So one of them has, one of them has an equation that seems to be mostly positive, or completely positive, mostly positive, at least in terms of the coefficients. And the other one, it seems to be mostly negative, right? So one of them is going to be the upward facing one, and one of them is going to be the downward facing one. So let's do a little conversion here, because we have a nice way of representing x squared plus y squared in polar form. X squared plus y squared is equal to r squared. So I could say r squared minus 3. And in this case, little intermediate step, factor out the negative, really a -1. And you have z equals 3 minus x squared plus y squared. So z is equal to 3 minus r squared, right? Now, both of these are the equations of parabolas. And in fact, any function that takes this form is going to be a paraboloid, right? So now, once we pare it down to a function of a single variable, that makes life a lot easier, because then we can rely on our knowledge of parabolas. So I look at this and say, well, this one opens up. in 2 dimensions, this one would open up. So I'll say opens up. This one opens down. All right. So now I know based on my diagram, you know, I'll try to use something bright. Try to use, see if it'll actually work where it actually takes the shape. Nope. Worth a shot. Now you're going to get what it looks like when I don't have autocorrect. Oh boy. All right, so the cross section here, so it's really these infinitely many circles with varying radii. Z is equal to r squared minus 3. And the other one, dude, let's see if this lime green shows up. Actually, on my screen, it's lime green, but on the Zoom screen, or at least on my laptop, it looks like puke green. So Z is equal to 3 minus r squared. All right, so that's what we're working with. Now we're going to get the volume of the region that's enclosed by those two figures, of the solid formed by the intersection of those two figures. Now I'm kind of looking at that, and my first thought is that it kind of looks symmetrical. So that's good news. Right? If I could just come up with the bounds there, then what I can do is I just figure out the top half. I mean, I can figure out the whole thing if I want, but if I just figure out the top half, then we're on easy street, because then I just double that and we have it. Right? So what we're going to do is first figure out the extremes here. All right, let's see, get this color going on here. I just need something that stands out compared to the rest of the graph. All right. So these are our extreme values. We need both of these puppies. Let me just do it that way. All right. So that would be the intersection of the two surfaces. Now, it looks like 2 points, but that is really going to be kind of like the hemisphere. I'm sorry, the equator. So what I can do is I can just set these two expressions equal to one another and solve. So r squared minus 3 would be equal to 3 minus r squared. It's quadratic, so let me get everything over to the same side. So we're looking at 2r squared, and that would be minus 6 equals 0. Common factor of 2, pull it out. R squared minus 6. 3 is what I meant to say. Factor, or, you know, add 3 to both sides, whatever, but the 2's gone, irrelevant. Either way, you know, if I add 3 to both sides, take the square root, I'm going to get the relevant r as being the square root of 3. Right? So yeah, plus or minus the square root of 3, but it's a radius. So, you know, the negative is just implying direction. We want the whole thing. Right? So this is a circle with a radius of 3. Radical 3 is what I meant to say. That's not a circle. Still not a circle. All right, that's a passable circle. All right, so this is the radius of radical 3. Now, when we're thinking in terms of polar coordinates, we want the angle, we want the radius. So this circular region, this base region, is going to start off at 0 and end at 2 pi. If I only want a part of it, then I would restrict it, but it doesn't seem that way. All right, so that's good news. So I think I got everything. I think I got my bounds. I think I got, yeah. All right, so when we set up our integral, what I would be looking for, so I'm looking at that lime green one. that part of it, I'm going to double that. All right. Because I'm just going to get the top half and then double it to get the bottom half to go along with it. The theta value is going to go from 0 to 2 pi. The r value, well, it's starting off at the center and working its way out from there. All right. When you're talking about the radius, always connected to the center. All right. So we're working our way out from the center, which is at 0. And the extreme value is radical 3. That's the furthest we ever get from center. All right. That lime green z function is 3 minus r squared. And then we get our r dr d theta. All right. So not too bad. Just got to do some work now. Not really a whole heck of a lot because this is, I mean, it's really just calculator work at this point. Let me get rid of some of this stuff. I do it in terms of x's because I didn't really draw the graph. All right, so function miscellaneous 0 root 3. I'm going to put the r first. So in this case, x, I'll just use x's. 3 minus x squared. I need an open paren here, so let me just tuck that in. Close the paren. Make sure it got what I need. Then chuck in a dx. That's 2.25. So I'm going to have 2 times over the interval of 0 to 2 pi, 2.25 in fraction form 9/4 d theta. The rest I can do by hand. So 9 theta over 4 over the interval of 0 to 2 pi. Whatever that result is, multiplied by 2. We don't need to plug in a 0, plug in the 2 pi, and I'm going to get 18 pi over 4, which is 9 pi over 2. Multiplied by the 2 on the outside, and we get a result of 9 pi. All right. So, not too bad. You know, I think most people are willing to take me at my word when I say, this is the easier way to do it. I mean, you're welcome to try on your own if you wanted to, just for fun. I'd never ask you to do it on the test. I did when I was a rookie, you know, teaching this course for the first time. I thought it would be fun, and I was wrong when I would say, you know, let's try it both ways. We'll do it in rectangular form and see how hideous it is, and then we'll get our reward, you know, and say, let's tackle this in polar form, you know, in cylindrical coordinates. And you know, it doesn't take too many examples before you realize, yeah, let's not do it that way. It's just too much. But the whole idea is, if you're dealing with circular graphs, then you want to be dealing with circular coordinates in some capacity, and your life becomes a whole lot more manageable when you account for that. All right. So that was 80 number 3. So let's take a look at 81 number 4. Compute the volume of the solid formed by the intersection of our surfaces here. And again, it's really the idea that we're going to convert these over into cylindrical form based off of some known relationships. Like we know that this is r squared, z equals r squared. That's an upward facing parabola, opens up. Now this one, square root of r squared, is just r. Right? I'll write the intermediate step. Z equals 2 minus the square root of r squared, which is really the same as saying z equals 2 minus r. All right, so that's a linear. Okay, so that's a linear relationship, at least as z and r relate to one another. right? So that part's okay. But based off of this diagram, it does look like, and it's kind of hard to see, but we are looking for an intersection. We got something going on over here. We're looking at some kind of cone. And some kind of surface based off of that. Maybe that wasn't the best idea what I just did, but we can see kind of tucked underneath is the rest of the paraboloid. And somehow along the way we have that intersection. Now we're looking again for the volume of the solid formed by the intersection of the surfaces. So it kind of makes sense to find the intersection of the surfaces and see what's up. All right. So that's what we'll do. We know that z is equal to 2 minus r. We also know that z is equal to r squared. So 2 minus r is equal to r squared. Bring everything over. R squared plus r minus 2 is equal to 0. Now, I'm going to just take the second here to show you this, even though it's very easy to factor. You don't need to factor, especially if it's been kind of a weakness. I know some people struggle and some people don't, but if you type in the expression, we're just looking for the intercepts, just tap on your intercepts and it'll tell you what the roots are. So you get r equals -2 and 1. Now this is, I don't know if this is exactly what we just did a few minutes ago, but it's very similar, right? You can do it that way. You don't have to do the factoring, right? Again, that's what I keep saying about it not being an algebra course. And then I go to grade the test and all I see is people, doing algebra. And I'm like, why? It's like, it's not helping anyone, right? Just making sure this isn't important. It's not, it is. Okay, so we have couple of ingredients here. Let me just plug in my iPad here because the battery's getting low, which is the #1 reason why I plug stuff in. I'll use the USB-C. Okay, so we had that going on. We're looking for the volume underneath one of the surfaces, but above the other, right? So that's kind of a tricky aspect. But once you kind of get an idea of which one's above the other, then you're kind of in good shape. And so when we talked about areas in 2 dimensions, finding the area between 2 curves, you found the dominant function and you subtracted from that the non-dominant function. So that's what we're going to do. So the one that is opening upward is the one that's beneath the other, right? So we're going to have a double integral. We'll worry about the bounds in a second. That's going to be related to the difference between 2 minus r and r squared. All right, so we're just doing a quick subtraction. And then that is going to get multiplied by r dr d theta. All right, so now I just need to consider what my bounds are going to be. All right, so the first bounds are going to be the r bounds. When we solve for r, we got 2 possible values of r. One of them was a -2 and the other was a 1. All right, an r value of -2, yeah, you can have an r value that's negative, but it doesn't seem to be relevant in this case. All right, because that would put us below the xy plane, and it looks like the relevant part of this is well, actually, no, it wouldn't put us below the xy plane. No, it's actually even simpler than that. I'm just making sure that it does actually make sense. Yeah. So, maybe I think the better way to do this, because I don't want to gloss over it. So let me just bring it up on Geogebra so I could actually point at it. Because if I hand wave my way through it, it's going to end up a disaster. Let me show you, get rid of the plane. We have z equals x squared plus y squared. And then we have z equals 2 minus the square root of x squared plus y squared. All right. So let me get a. All right. So that's what. Actually, this figure looks a whole lot better than it used to. I'm going to snag this one. I'll take it as a typo. This diagram, whatever they did, maybe it's the mobile app. I don't know, but this diagram looks a whole lot better than the one I have. All right. So yeah, the typo would be on page 81, change the diagram for number 4. All right. So something pretty simple. So, oh, geez, I definitely feel the frog in the throat coming back. So we're looking at, again, an R value of possibly a -2 or a 1. All right. So let's focus on, first up, the theta is obvious. So it's going to be 0 to 2 pi. All right. That's because you're going around the whole way. And when I have it in motion, it makes it even more obvious. All right. So that part's good. Now, in terms of the R values, if you look at the z-axis, you could it's hard to see, but you could kind of see it there, right at the 2. It looks like you have a z-intercept of 2. All right. So there's that part of it, and then if you kind of look around underneath, all over the place and here, there, and everywhere, the only reference you can kind of get to a 2 in any capacity would be along that z-axis, right? Which doesn't make sense based on what we need. What we need are the outer extremes. So if we kind of look at it as a as kind of a projection onto the xy plane, it makes it a little bit simpler to understand that, yeah, the diameter might be 2, but the radius is going to be 1. The furthest you're going to go out from center scale-wise is going to be 1 unit, right? So it's kind of like if you were to make a sphere with the center at 0, 0, 1 with a radius of 1, what it would do is it would encapsulate that coordinate on the high end, 0, 0, 2, and then it would get the 2 values on the sides, well, actually along that entire ring, and it would also get the bottom of that paraboloid, right? So that 2 is referencing, essentially, long story short, it's referencing something we don't need, all right? So what we do need is that circular path. Now, this might be the best angle because that inner circle there, you can see that, I mean, just looking at it from this perspective, you can see that that's 1 unit, right? And so that's where we're getting the idea that the 1 is the relevant value, the -2 isn't, right? So we're not tossing the -2 because it's negative. You could have a negative radius. It just means you're going the other way. The other way from what? The other way from the angle that you're facing, right? So if you're facing 0, you're just going 2 steps towards pi, all right? If you're facing pi over 4, you're going 2 steps towards 5 pi over 4. In this case, we're not tossing the negative again because the -2 because it's negative. We're tossing it because it's not relevant, right? So the radius is going to go out. The relevant radius is going to go out from 0 to 1, right? So once we have that, we're in good shape because now everything is calculated, all right? So if you want it to be 0 to 1.
Professor, can you explain why is it going to from 0 to 1 again?
Because, yeah, 1 second. Because if you look at this pinkish circle on the inside, you can see that it's going 1 box in every direction.
Mm-hmm.
And that's the furthest, if you're looking at the intersection here, that's the furthest out from center that we need to go in order to cover the relevant part of the graph. Right.
Mhm.
So if I bring this in, just show it, I'll just snap it in there.
Okay, gotcha. Thank you.
I'm just going to bring it in and mark it up anyway, though.
Mhm.
Save to flow. This one I actually do need to save. Actually surprised this graph came out so nice on the mobile Geogebra. Get out of here, ugly graph. I got a good looking one. All right, so yeah, it's this piece here. So going here, here, and then down and around. So it's kind of like that little the little hat there. So what we're looking at is the furthest that we go from center in any of these directions here. Because it's circular, it's going to be 1 in each direction. All right, so that's why we chose the 1. All right. So then we pop it into Desmos. 0 to 1.
Thanks.
Yeah, no problem. So x paren 2 minus x squared. Close them up twice. I got the x for this that r, the r d theta. So I'm going to put in a dx now. So that gives me something that's rational. So 5/12. 5/12. That's being integrated over the interval of 0 to 2 pi. D theta, so 5 theta over 12 over the interval of 0 to 2 pi. So we're talking 10 pi over 12, which reduces to 5 pi over 6. All right, so the computation is really nothing significant because, one, we're having Desmos do a lot of it for us, but even still, it's reverse power rule. If we had to do it by hand, it's still not something that I would hope people would be finding, I don't think anybody's finding that challenging. All right, so that's 81 number 4. Let's see, I think there was another, yeah. And I just want to get a look ahead and see if there's anything else after that. Yeah, I think that was the last one, the last starred problem, but then we've cleared the ledger here. Is 83 number 3. All right, so this one's talking about a triple integral, which kind of makes sense. We're on the triple integral page. Evaluate the triple integral of the function over the solid tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and the plane x plus y plus z is equal to 1. All right, so we're in the first octant here. Right, so it's basically saying you get the whole plane, but we're only focusing on the part of it that lives in the first octant. Right, so that simplifies things, which is good. But we are looking at the unit cube rather than the unisphere. All right, so it's going to be a triple integral, and it's going to be under the function, bounded beneath the function 5x, is it 5x minus 3y. Now our bounding is going to be, it's going to be a choice. It's like what makes the most sense. We tend to want to have, it's anytime you're in rectangular form, you want to have the most complicated bounding as the innermost bound, then less and less complicated until you get to the straight constant bounds. All right. So it's restriction upon restriction upon restriction. So first your restriction is based on a multivariable function, then it's based off of a single variable function, and then it's just based off of constant bounds. All right. So we got to look at what we're up against here. It's bounded by x equals 0, y equals 0, z equals 0, and this plane. All right. So that plane, let's start with that. I'm just going to kind of tuck that off on the side. X plus y plus z. is equal to 1. All right. So if I want to take care of my z bounds first, I could do my dz, then I would want to solve this for z in terms of x and y. So 1 minus x minus y. Right. Now, our bounds are the planes x equals 0, y equals 0, z equals 0, which is great news because that's telling us that we're looking at the xy plane, which is the floor, and then the z plane of z equals 0, which is essentially the wall, right? So, well, actually, one of them's the wall. The other two are the floor. Z equals 0 would be the floor, right? So from the ground up, z equals 0 up onto z equals 1 minus x minus y. So that would be my first set of bounds. All right. So the next set of bounds, a little bit more interesting. We're looking at a choice between x or y. So let's say we want to do it with respect to y. At this point, it doesn't matter, and you'll see why in a sec. So let's say we're looking at this function, and we want it to be on the xy plane, right? That x plus y plus z equals 0. If I want that on the xy plane, that means z is equal to 0. All right, so the part of that graph that's on the xy plane would be 0 equals 1 minus x minus y, which means y equals 1 minus x. All right, so if we look at that graphically, just going to do a quick sketch. 1 minus x, y-intercept of 1 with a slope of -1. So 1, 1, draw a line. Something like that. Do a little bit better. All right, so that little triangular region, we got to be thinking of as, okay, well, we want to be bounded by the function. So in terms of y equals 1 minus x, that's this guy, and y equals 0, that's this one. So that's telling me, if I really bring it in, that I'm going up the ladder here, but I'm capped off based off of the line itself. Now, the issue that we kind of run into is, and I kind of oversimplify this, and it's never a good thing, but when I say that I'm going from 0 to 1 minus x, what I'm really looking at is this. And this might be the missing ingredient for good understanding of the concept, because this is something that I'm kind of, and I think a lot of teachers are, I know it, definitely me. You know, I don't want to damn everybody else, but I'm definitely guilty of it. I kind of gloss over this part of it. So we're saying that we're going from the line y equals 0 to y equals 1 minus x. So that would give me all of this, all right, with no restriction on the left end. On the right end, it's capped. It's capped at whatever the line y equals 1 minus x caps it at, or wherever 1 minus x caps it at, right? So that's fine, but that's going to give me infinite amount of area that I don't need. But that's one set of bounds that I have accounted for now. I can say that I'm going from y equals 0 to y equals 1 minus x. And I'm just going to try to give myself a little bit more room. It's the last set of bounds that restricts that restriction, because we're restricting it, to overuse a term, we're restricting it a piece at a time, you know, one variable at a time. So the first restriction was to say, okay, we're living in terms of z from this level to this level. Now, just looking at the xy variable, that relationship, just focusing on the y, we're going from 0 to 1 minus x, but that didn't restrict it enough. Now, if I really truly want to restrict it to this triangular region, what I would have to do, get blue in here, is now cap it so that it's only going from 0 to 1. All right, because I need it to only be living in that triangular region. If I want to cap it, I need it to only account for this piece. I have to restrict my restriction so it only goes from 0 to 1. I can make these vertical lines look vertical. Oh. Right, that one I might have to live with. Okay, actually got it. All right. This way I don't account for all that extra green horizontal line. That stuff's unnecessary. And it's overkill. So what I have here is the appropriate triple integral. All right. Now, I've been kind of like encouraging the use of Desmos to the point where I'm saying, oh, we gotta have the dx in here, where I'm saying, listen, let's avoid trying to do stuff like this by hand. I can say that this one is kind of a nightmare if we have to do it out. So what I'm gonna say is, I'm gonna get a little sneaky here. I'm gonna say let's change the directions of this problem, because the big challenge here is not your ability to integrate. I'll get you on that. The ability to come up with the appropriate triple integral is really what the whole point of this question is. So I'll take it as a typo. Write the triple integral that would be used to find the volume bounded by the function blah 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 over the solid tetrahedron bounded by blah blah blah. I'm using bounded by a couple of times, but it is what it is. So yeah, so the typo is, if you want to keep it simple, oh, somebody's already got it anyway. But yeah, to keep it simpler, just change the directions on number 3 on page 83. All right. So that was really the purpose of the problem, because otherwise we get bogged down in the computations. That's really not what it's all about. Right. So moving along, moving down the line. 88, number 3. All right. So this is going to kind of support what I did in the video I sent out today. So if you didn't get a chance to look at that, you'll have an opportunity to look at it. It's on YouTube. So so definitely take that opportunity, but you'll also have the ability to kind of pick up some of the info right now. All right. So set up an integral for the volume of the region bounded by the cone and the sphere below. And so very simple set of instructions. The minute you hear the word sphere in a problem, that's your indication to go spherical coordinates. All right. On the test, I really can't see myself saying for this kind of question, I don't remember in the previous versions, the pencil paper. Some cases I say to do it with spherical coordinates or cylindrical or whatever, but I can't see myself moving forward saying to do it one way as opposed to another. It just doesn't seem necessary. And like, it's got a sphere in it. Why wouldn't you use spherical coordinates? So just think of it that way. But this is a pretty nice looking graph. I think it gets the job done in terms of what you need. So I mean, we got a lot of stuff going on here where we need to convert it over and all that jazz, but you know, it's pretty clear what the bounded region is talking about. It's gonna look like a little ice cream cone. You know, you got the cone there, then you got the little extra fringe on the top there. All right, but all we need is the you know what? I'll take it as a typo. Set up. It wouldn't be an integral. You could say an iterated integral, or it would be a triple integral. All right, so let's say an iterated integral. All right, I like using the word iterated. Not, you know, you see that in textbooks a lot, but I like it because it gives you the luxury to choose between a double integral, a triple integral as needed. All right, it's just a little extra where you're like, well, I can do it with a double integral, but it says to do it with a triple integral. Why do I have to do it that way? I can do it easier this way. You know, that's just my thinking there. So anyway, we need a couple of things. We need some conversions. We'll start with that. Now, at first glance, I got my two equations here. I'm just going to rewrite them. All right. So let me just kind of bring it in a little closer. We're looking at z equals this ability to draw a straight line is done by 3x squared plus y squared. And then z equal 4 minus the square root of x squared. I'm sorry, the square root of 4 minus x squared minus y squared. All right, so in the first case, we have a 3 that can be factored out of the radical as a radical 3. All right, so we're looking at z equals radical 3 radical x squared plus y squared. We'll hold that thought for a second. For the second piece, I have a negative that can be factored out. So 4 minus x squared plus y squared. That might be helpful. We'll see in a minute. It's kind of like, you know, what are we going for here? Well, in the case of the second function, it looks like it's shaping up to be a sphere. So I'm going to square both sides. And then I could add this quantity to both sides, and I get x squared plus y squared equal, plus z squared is equal to 4. All right. So that gives me rho squared, because x squared plus y squared is equal to rho squared is equal to 4, which gives me rho equal to 2. All right, looking at the diagram, that holds up. Now, that being said, you really kind of didn't need to do any of that if you just looked at the picture, all right? Because if you know that a sphere is defined by its radius, this one pretty clearly has a radius of 2. All right, so if you could pick it up off the picture, that's even better. Sometimes, you know, force a habit and just kind of dive right in, and that's how it goes. But you know, it kind of is what it is. All right, so a nice little relationship that we get from this is, if you look over on the side, and there are important rules. We know that z is equal to rho cosine phi. And we also know that the square root of x squared plus y squared is equal to rho sine of phi. So rho cosine of phi is equal to radical 3 times rho sine of phi. I mean, that's pretty good substitution there. I can bring everything over to the same side. All right, I guess I don't need to keep zooming out. Bring everything over to the same side. I get rho cosine of phi minus root 3 rho sine of phi equals 0. I got my common rho. I can pull that out. You got rho times cosine of phi minus root 3 sine of phi is equal to 0. Now, a couple of ways we can handle this, but one thing before we go too crazy with the trig is we're looking at a quadratic relationship, product of two factors. So I can say rho is equal to 0, which is great news because now I have the bounds for rho. So that's awesome. And I'm on my way to finding the bounds for phi. Now, I think, you know, and you can do the work if you want, but just by looking at the picture, this looks like for theta, it looks like we're going all the way around, right? And if you really kind of emphasize it, just, you know, pick an important part, especially when you look at the intersection, it looks like theta is going to be one full turn around the circle, right? Around that that unit circle, right? No matter where you slice it, that's how it's going to be. Now, in terms of the phi value, different story. It's definitely not going to be one full turn. Phi is the angle formed with the z-axis. So the furthest it goes out is this angle here. I don't know what that angle is, but it definitely looks like it's acute. All right, so I'm on the lookout for some acute angle, right? And in fact, if you kind of look at it as this angle created gives us an intersection, that intersection traces out that circular path. Right? So in that regard, it's kind of cool. It creates kind of sort of like a hinge. But ultimately, it's the phi that we're looking. I keep doing that. Just turn off the line draw tool. Right? It's that phi that we're looking for. So we're looking for an acute angle. All right. So that's what we're going to find. I'm sure we're going to find. So it's a trig relationship. You know, pick your favorite approach. I don't know. It doesn't look like we have a common factor to pull out. I can add a root 3 sine of phi to both sides of the equation if I want. I mean, that's not a terrible idea. But what I could do instead, let me go back to the color coding that I was using, is I can divide out one of the trig functions here. All right. So if I divide, let's say I want to free up that radical 3, I can do that by dividing each term by the sine of phi. All right. So divide each term by the sine of phi. And I get cotangent of phi minus radical 3 is equal to 0. Cotangent of phi is equal to radical 3. Now, if you don't happen to know off the top of your head your cotangent relationships, then you can take the reciprocal of both sides. Reciprocal of cotangent is tangent. Reciprocal of 1 over radical 3 is 1 over radical 3. Either way, you're going to have to know some kind of fact, right? So phi is going to be equal to 30 degrees, well, pi over 6 if we're going in radian form. Right? So if you know your unit circle trig, you're going to be in pretty good shape. We know that phi starts off the z-axis and expands outward from there. So we know it's spanning from 0 to pi over 6. All right. So it's really just a question of, all right, well, now what? Triple integral. We know the thetas are going from 0 to, I'm going to do that in blue, 0 to 2 pi. Yeah, that's one full turn around the unit circle. We know the phis are going from 0 to pi over 6. And we know that the row, which I'm doing in this funky green color, is going from 0 to 2. Rho squared sine of phi for our unit sphere to build up, based off those unit spheres, all the space restricted by those bounds, d rho, d phi, d theta. Okay. There's no other variable, there's no fourth variable involved. So it's just a single unit sphere propagated out through that interval. That's going to come up, that's going to help us come up with that bounded, triple integral, a bounded region. Right. And so, I mean, carrying out the computations is not difficult, but it's beyond what the question's asking us to do, so it's unnecessary. So that's all we would need. Right. So it's pretty not bad when it comes down to that. Yeah.
How did you set up the integral to be p squared sine theta, or that sine? I forgot the name of it.
Oh, the rho squared sine phi, yeah, all that stuff, that's built into the formula.
Okay, got it. Thank you.
No problem. All right. So as far as that's concerned, that's all she wrote. Now, if it said something like determine the mass over the interval, you know, where they gave you a mass function that's a multivariable function, then it's a different story. You know, then you'd have something to integrate beyond the rho squared sine phi, etc. Right? But in this case, it's just that. Right? So the beauty of the spherical coordinate system is if you're just looking for volume, it really is just based off of whatever the bounds are. Once you come up with your bounds, you're pretty much done, and that's really it. All right. So that's the case of the spherical coordinate system. Now let me stop this recording.